There is a way to purify dirty water using nothing more than two simple pieces of metal. No electricity, no plastic cartridge, no battery, and no chemical tablets. Just copper and zinc touching each other inside contaminated water, setting off a reaction that begins almost immediately. As that process starts, bacteria begin to die, chlorine begins to vanish, and certain contaminants begin attaching themselves to the metal surfaces. It sounds almost too simple to be real, especially in a world where clean water is usually tied to expensive devices and constant replacements. That is what makes this story so striking. We've been conditioned to believe that safe drinking water must come from complex systems, branded products, and filters that wear out every few months. But what if one of the oldest purification methods in human history was also one of the cheapest and easiest to understand? What if the real question is not whether it works, but why so many people were taught to forget it? This is the story of a purification method that stayed in plain sight for thousands of years, survived across civilizations, and then slowly disappeared from everyday knowledge. And once you see how simple it really is, the silence around it starts to feel impossible to ignore. Long before modern filter companies, ancient civilizations had already learned that copper could help keep water safe. In ancient Egypt, around 2400 BC, muddy river water was poured into hammered copper vessels and left to rest through the night. By morning, the water was cleaner, clearer, and trusted enough. This was not treated as myth or superstition. It was recorded in the Smith Papyrus, one of the oldest medical texts ever discovered, as a real method for sterilizing drinking water and for treating wounds. The Greeks later recognized the same truth in a very different setting. On long sea voyages, water stored in wooden barrels spoiled quickly, turning foul and dangerous. But water kept in copper containers stayed drinkable for far longer, even under the brutal Mediterranean sun. The Romans then pushed this principle further, using copper in water systems, medical treatments, and military life. Again and again, the same pattern appeared across the ancient world. People may not have understood bacteria or chemistry, but they clearly understood the result. Water connected to copper was safer, and that knowledge was too consistent across centuries to dismiss as coincidence. What makes this story even more powerful is that the knowledge was not limited to Egypt, Greece, or Rome. On the other side of the world, the Aztecs, with no contact at all with the Mediterranean civilizations, also discovered the value of copper. They used copper mixtures for sore throats and infused water with copper in ways connected to healing and protection. Two worlds separated by oceans and centuries still arrived at the same understanding. That kind of agreement across distant civilizations does not feel like chance. It feels like people repeatedly observing the same truth in real life. India preserved that truth in an even more continuous way. For generations, Hindus stored holy water from the Ganges in copper vessels and kept that tradition alive across the centuries. Modern testing later examined this practice under controlled conditions and found that water stored in copper for 16 hours showed a dramatic reduction in harmful bacteria, including dangerous organisms such as E. coli, salmonella, and cholera-causing bacteria. What ancient people trusted through experience, modern researchers were finally able to measure. By this point, the pattern becomes impossible to ignore. Civilizations that never met, never traded ideas, and never shared scientific language still came to the same conclusion. Copper helped make water safer. And when the same discovery appears again and again across thousands of years, it stops looking like tradition alone and starts looking like a law of nature waiting for science to catch up. For thousands of years, people could see the effect of copper, but they could not explain the mechanism behind it. Modern science finally gave that old knowledge a language. When copper comes into contact with water, it releases positively charged particles known as cupric ions. These ions do not simply drift through the water without purpose. They attack microbial life directly, breaking through bacterial cell membranes, disrupting vital enzyme activity, and interfering with the organism's ability to reproduce. In other words, the metal is not passively sitting there. It is actively working against contamination at the microscopic level. That is why the old observations from Egypt, Greece, India, and other civilizations matter so much. They were witnessing real chemical effects long before chemistry had the tools to describe them. Modern studies later confirmed that water stored in copper vessels for enough time showed a major drop in harmful microorganisms. What once looked like ancient practice or inherited custom now stands on a scientific foundation strong enough to be tested, measured, and repeated. And this is where the story becomes even more interesting, because copper alone is only part of the explanation. Once copper is paired with zinc, the process no longer remains just an old purification habit. It becomes a far more powerful electrochemical reaction, and that is where this buried method takes on a completely different level of importance. The real breakthrough comes when copper is combined with zinc inside water. Zinc is more reactive than copper, which means it gives up electrons more easily. When the two metals touch while submerged, electrons begin flowing from the zinc to the copper, creating a small but continuous electrical current. You would never feel it with your hand. It is nowhere near strong enough to power a device, but it is powerful enough to intensify purification. What forms is a galvanic cell, the same basic electrochemical principle that powers a battery. In this reaction, zinc acts as the anode, sacrificing itself by releasing electrons, while copper acts as the cathode, receiving them. The water itself becomes the electrolyte. This allows the whole system to function. Instead of generating useful electricity for a machine, this tiny current helps drive a steady release of charged particles that attack contaminants. Bacteria are damaged, chlorine is removed, and certain heavy metals begin bonding to the metal surfaces. What looks like a crude combination of scrap materials is actually a compact electrochemical system, working silently inside the container. This is exactly why the idea becomes so hard to dismiss. The moment copper and zinc are paired, the method moves beyond ancient observation and enters the realm of measurable modern performance. It is no longer just a story about what older civilizations seem to notice. It becomes a system with clear scientific logic behind it. And that sets up the next question. How well does it actually perform compared to filters today? In 1984, Don Heskett stumbled into a modern demonstration of what ancient civilizations had already understood in practice. He dipped a brass pen into chlorinated water and watched the chlorine disappear. That moment was small, almost accidental, but its meaning was enormous. Within a few years, he had secured a patent, and the principle attracted serious scientific attention. What earlier cultures had learned through repeated experience was now reappearing in a form modern institutions could no longer dismiss as folklore. The same core idea also appeared in one of the harshest environments humans have ever entered: space. NASA developed water purification systems based on metal ion released to protect astronauts from bacterial contamination. Proving this was not just some rustic survival trick, but a serious scientific solution trusted under extreme conditions. Years later, in 2008, the EPA officially registered hundreds of antimicrobial copper alloys as proven to kill harmful bacteria on contact. That marked a rare moment when a major modern authority confirmed in formal terms what history had been saying for thousands of years. By this point, the story is no longer built on ancient testimony alone. It stands on history, modern testing, institutional recognition, and repeatable chemistry. And once all of that evidence is laid side by side, the next part of the story becomes even harder to ignore: the numbers. Once the performance is compared directly with modern commercial systems, the economic side of the story becomes almost impossible to overlook. A copper-zinc filter medium, such as KDF, can remove 99.9% of free chlorine on contact, capture heavy metals like lead, mercury, chromium, arsenic, cadmium, iron, nickel, and aluminum, and also help control bacteria, algae, and fungi through the ongoing galvanic reaction. A standard activated carbon filter, by contrast, usually needs replacement every few months, depending on how often it is used. The difference is not just technical. It is financial. Over a span of 6 years, repeated carbon filter replacements can add up to hundreds of dollars. A small amount of copper and zinc costs only a fraction of that and can remain effective far longer with basic maintenance. That is what gives this story its real force. The comparison is not between two systems that cost roughly the same. It is between a low-cost method built on common metals and a commercial model that depends on constant replacement. The more closely you look at those numbers, the harder it becomes to believe that this method faded away because it was weak or impractical. It starts to look like something else pushed it out of sight. That brings us to the ugliest part of the story. If copper and zinc can purify water effectively, last for years, and cost very little, then they are a terrible fit for the business model that dominates the modern water filter market. That market is worth tens of billions of dollars and depends on one thing above all else: repeat purchases. You buy the pitcher, then the cartridge, then another cartridge, and then another year after year. What looks like a product is really a subscription in physical form. A purification method made from two common metals does not fit into that system, because it does not keep customers buying replacements every few months. And that is why this method did not need to be openly banned in order to disappear from public awareness. It only needed to be pushed to the margins, treated as outdated, or ignored long enough for people to stop thinking about it. Copper cannot be patented. Zinc cannot be patented. The basic principle is too simple, too old, and too widely available to be turned into a tightly controlled source of recurring revenue. Meanwhile, modern systems such as carbon filters and reverse osmosis units continue to be sold as the standard, even when they require repeated maintenance, costly replacements, and in some cases, significant water waste. When a cheap method works for years and a costly one must be repurchased again and again, the financial incentive becomes painfully obvious. So the real issue may never have been whether this method worked. The deeper issue is that it worked too well while making too little money. And once that possibility enters the picture, the final question becomes unavoidable. What can this method actually do in real life? Where does it fall short? And how would someone use it today? To be fair, copper-zinc purification is not a perfect answer for every kind of contamination. On its own, it does not remove every organic chemical, especially certain pesticides, and it is not fully effective by itself against parasitic cysts such as Giardia or Cryptosporidium. That matters because credibility depends on honesty. This method is powerful, but it is not magical. Its real strength is in removing chlorine, reducing heavy metals, controlling bacteria, algae, and fungi, and doing so with a lifespan that far exceeds most disposable filter systems. In practical use, the method is remarkably simple. Water should first be poured through cloth to remove visible dirt and sediment. Then a twisted pair of bare copper wire and zinc metal is placed into the water and left there for several hours, with longer waiting times producing better results. After that, the treated water can be passed through a basic carbon stage, such as crushed charcoal held in a simple makeshift filter. In the original example, this creates a two-stage system. The copper and zinc handle the biological side and much of the heavy metal burden, while the charcoal helps deal with remaining chemical impurities. For more permanent setups, granulated copper-zinc media such as KDF can be used in a gravity-fed filter body for long-term treatment. And that is what gives the story its final weight. Ancient Egyptians trusted copper to protect the wounded. Greek sailors relied on it at sea. Romans built it into daily life. Aztecs, Indians, modern researchers, NASA, and the EPA all arrived at evidence pointing in the same direction. The knowledge never truly disappeared. It was preserved in fragments of history, in scientific papers, in patents, and in overlooked technologies, waiting for someone to connect the pieces again. What died was not the method itself. What faded was public memory. And now that memory has been opened again,